Good day, I'm J Wildberger. In today's video, we're going to be taking Boolean algebra and moving it into an important application in the 20th century. This is Shannon's circuit analysis. So this is the start of applying classical logic via the algebraic formulation of Boole and then Venn and Peirce to the 20th century revolution in computer science, generated by understanding circuits and then transistors and logic gates eventually. So the story today is maybe a little bit novel because we're going to be looking actually very carefully at Claude Shannon's original paper, and there's certainly some surprises there. Okay, so to remind you, the basic setup is we're talking about the algebra of Boole, or almost equivalently, but not quite the same, Boolean algebra. So with the algebra of Boole, we have these operations of addition and multiplication mod 2. And with the Boolean algebra, we have three operations. We have the V here, and the wedge, and the bar. Okay, so in terms of gates, this is the OR gate, and this is the AND gate, and this is the NOT operation. Now, because we consider the algebra of Boole to be primary, we're going to reserve the addition and multiplication operations for the basic operations here. And that means that these operations have sort of secondary names. So either with the V's and wedges, but sometimes also with some variant sums and products. So we'll also allow that P or Q is written as P circle sum Q, and P and Q written as P circle product Q. But since this operation and this one here are the same, we'll also allow ourselves to write just ordinary multiplication with just juxtaposed elements there. In terms of alternate notation for the complement or the negation, with a bar on top or maybe a little bit of a twiddle there in front of it, or Shannon actually uses a prime to denote the negation. Okay, so these are the ingredients, and now let's have a look at the Boolean algebra and slowly how it developed into a powerful tool for 20th century circuit analysis. So an important precursor to this development is an influential paper by Edward Huntington in 1904 called Sets of Independent Postulates for the Algebra of Logic. Now, this paper introduces Boolean algebra in a rather abstract fashion. So this is an important kind of development in 19th century mathematics, the realization that there's an idea of abstract algebraic structures out there. And often the kinds of things that we study initially in some contexts can actually be generalized very widely, and that gives us sort of a bigger picture, and often we get at the essentials of a subject and not sort of obscured by details. So that's what he did. He said, okay, what's really happening with this algebra of Boole? We have these zeros and ones, and we have these operations, but at some level you can just think about the operations as being somehow the basic ingredients and forget about what actually the nature of those operations is. Just study the operations and their properties. So the way he did that is he said, okay, let's start with a class of elements, A, B, C, dot, 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 and we'll call that K. Now this kind of thing makes us nervous because we don't know what those three dots mean. But for our point of view, let's just consider that this is some finite collection, okay? So it's a finite collection of objects that we know all about. Okay, now we're going to introduce two binary operations on this collection. The first one is a sum with a circle, so a circle sum, giving us A circle sum B, if A and B are in here. And the next one is a circle product, so A circle product C, again with two elements there. So these are binary operations. They take two elements in our given class or set, and they produce another one. Then there's a unary operation, unary as opposed to binary, meaning that it only accepts one object as an input. So it takes one of these things and churns out another one. This is the bar operation, and so if D is an element here, then D bar is this operation. Okay, so we're just going to assume that we have these things subject to some certain properties. or as Huntington said, certain postulates. We're going to assume that these things obey certain laws which mimic those that are valid for the Boolean situation. Okay, so now this structure that we have, the set, and then these two binary operations, and then this unary operation, that all together is a Boolean algebra, says Huntington, if various properties hold. And here I'm listing the standard ones, not exactly the same way Huntington did, but he was sort of interested in finding a minimal set of postulates from which you could deduce the other properties. And in fact, he, in his paper, suggested a number of different possible sort of starting points for the initial postulates that we assume. But one way or the other, we want these properties to hold. So let's just review them. We need the commutativity of both the sum and the product. We need associativity of both of those. And then crucially, we need distributivity, but two of them. So there's two distributive laws. One is sort of the standard one, like A times B plus C is A times B plus A times C. But also the second one, which is very unfamiliar to us in ordinary arithmetic, but we understand it from a set theoretic point of view, that A plus B times C is A plus B times A plus C. Then we also have some special elements, 0 and 1, that have certain properties. A plus 0 is always A times 0 is always 0, and A times 1 is always 1. And in addition, this bar operation should satisfy that A plus A bar is always 1, and A times A bar is always 0. And one more property having to do with the bar, what happens if you apply it twice, so A bar bar is back to A, and that's involution. Okay, so these are properties that ultimately are associated to a general Boolean algebra. If we have these properties satisfied, then we have a general Boolean algebra. And we don't really need to inquire as to the nature of these operations. That is, we don't need to know what they actually are. The only crucial thing is that they obey these properties. This is very much the abstract point of view towards algebra that became very prominent and important in the latter half of the 19th century, and then very important in the 20th century. Okay, and now we come to the central figure here, which is Claude Shannon, who lived from 1916 to 2001. An American electrical engineer and a brilliant fellow who not only introduced the connection between Boolean algebra and circuit analysis, but also went on to found information theory, which is also a very hugely important development in the modern world. Okay, so this first paper, this 1938 paper, very famous, a symbolic analysis of relay and switching circuits. This was basically the content of his master's thesis, which he wrote at MIT. And I think it was motivated by actually having taken a philosophy course as an undergraduate and making this connection that the logic that was developed in this philosophy class was really very useful for logic circuits. Although I may have to say that Charles Peirce also had some idea in this direction. He wrote a letter where he also suggested the possibility of doing such a thing quite a few decades earlier. But Shannon just laid out how do we actually do this. So we get an important connection between Boolean algebra and circuit analysis. Okay, now it's a surprise to me to actually have read this article. I haven't read the whole thing, but I've looked at the relevant sections. And so it turns out to be quite surprising because his take on things is very unfamiliar if you're used to the standard story that we learn these days in electrical engineering. And partly this is perhaps because this paper was pre-transistors. Transistors were only introduced around 1947. So this is before that. And so logic gates hadn't come into play. But also because Shannon sets things up in a somewhat counterintuitive, almost reverse way from what we would perhaps naively think. So he's interested in circuits, we've got wires, and we've got switches like relays that turn on or off. So for example, here's a part of a circuit and there's a gap there. And maybe the gap can be closed and maybe it is not closed. And he associates with this this sort of terminal here, a quantity called x, say, which depends on the endpoints, which he calls the hindrance. So the idea is he's interested in what obstruction is there to current flowing here. So obstruction, same as hindrance. And he says that if there's no obstruction or there's no hindrance, the hindrance is 0, that means that we can actually pass current through there. The circuit is actually closed. On the other hand, if the circuit is not closed, if it's an open circuit like this and current cannot flow, then we say that the hindrance is 1. So this is a little bit opposite from our usual thinking. Okay, so x equals 0 means closed circuit, means that the current can flow. X equals 1 means open circuit, the current cannot flow. So this is not measuring whether the circuit is on or off, it's measuring whether the hindrance is off or on. That takes a bit of getting used to. It's quite interesting. So that's the starting point, this concept of hindrance, and he's interested in analyzing big circuits and seeing how we can understand how these hindrances combine. So there are two basic relations that these terminals can have with each other. They can be in series or in parallel. So if we're talking about series things, we have a gap there and we have a gap there. So here there's a hindrance of, say, x, and here there's a hindrance of y, and together that collectively constitutes another situation, and he says, let's call that x circle sum y. Okay. So the properties here are that if these are the values of the hindrances of x and y, then the hindrance represented by x plus y will be given by this. So let's have a look at this. So if x and y are both 0 hindrance, now that means, I remind you, that these are both closed, okay? So the effect of that is that circuit can go through. So in other words, that the hindrance of this thing will be also 0. On the other hand, if one of these is having a hindrance of 1, if one or both of them are having a hindrance of 1, then that means that circuit is not closed. Cannot have a flow here, and so the net effect is to have a hindrance of 1 in the sum. Okay, the other situation is when we have sort of parallel hindrances like this. So here's a hindrance of x, here's a hindrance of y, and we have this sort of branching parallel situation, and so we represent that with this other operation times, with, say, a circle around it, x times y. And then here are the values of that. So if one of these two, one or both, are closed, in other words, have 0 hindrance, then the whole thing will have 0 hindrance because current will be able to flow. Okay, so if one of these is 0, either here, here, or here, then we're going to get 0 hindrance for the product. And only when they're both open, in other words, hindrance of 1, then the whole thing will have a hindrance of 1. So it's curious because this is kind of opposite our usual intuition, at least my usual intuition, with regard to, what open and closed and on and off mean with regard to electrical circuits. Okay, so the thing to remember is that the series connection corresponds to a sum, series sum, and the parallel connection corresponds to a product, parallel product, in Shannon's original formulation of things. Now there's one more operation in the story, which is the complementation or negation. So this is just very simple, that we just take a terminal and we do the opposite of whatever it is currently doing. So for example, if x here is open, so there will be a hindrance of 1, then here x bar will be closed and there will be a hindrance of 0. On the other hand, if we have y with a hindrance of 0, current can flow, then y bar has a hindrance of 1, current cannot flow. Okay, so there's the little table for x bar. Okay, and now Shannon recognizes that this is essentially Huntington's Boolean algebra, that these operations that we have going here, which are, of course, familiar to us. But he recognizes that this is the same as this abstract formulation that Huntington had set out. And so he's in a position now to apply this logic or algebra in order to simplify complicated circuits. Unfortunately, his paper does not actually reference Boole. He doesn't actually even reference Boole. He references Huntington's paper. And so maybe he was not aware of Boole, I don't know. But in any case, the history of 20th century electrical engineering would possibly have been quite different if he had read Boole's first paper in the story and realized that there was another way of describing what's going on here, or at least accessing or working with the algebra here. But nevertheless, you can see that it's natural to have this Boolean algebra point of view here, because these operations are very sort of natural ones, series and parallel, and we get the and the or operations. So it's not a surprise that the Boolean algebra plays a role. Okay, so here's an example that Shannon actually looks very carefully at. It's a rather complicated thing. Let's have a look at it. We see in particular that there's these hindrances here, but also their bars are appearing in other places. So here's W, and here's W bar, and here's W bar again. So how are we supposed to interpret this? Well, the meaning is that we can turn these things off and on sort of simultaneously. So you can have an operator perhaps somewhere, and he has a switch in front of him where he can turn the hindrance of W on or off. And that will then simultaneously affect this terminal, and this terminal all at the same time. So when this one's got a hindrance of 1, in other words, the gate is like open, then this one will have a hindrance of 0, and this one will have a hindrance of 0. These will be closed, and current will be able to pass through here, but not through here. Okay, so we have this whole thing here, and then it's a straightforward exercise to convert this into a algebraic expression involving these operations of addition, circle addition, and multiplication, or circle multiplication. Now, to make that easier, we're going to replace the circle multiplication with just an ordinary product, okay, because that does actually correspond to our algebra of Boole product. Okay, but we'll keep the circle sums just to remind us that this is the Boolean story, not the mod 2 arithmetic of Boole originally. Okay, so how do we read this? Okay, well here we have a W, there it is there. And then this thing here, this whole thing here is in series with W, so it's connected to it with a plus. And then this whole thing here is, well, there's a parallel here, there's the W bar here, and that's in parallel with this, so we have to multiply. And this little series here will be a sum, so that's x plus y. And then we have to add the result of all of this. This is the result of essentially 3 channels, okay? The channel x plus z, that's representing here. This is x plus z representing these 2 things which are in series. And then we have s plus w bar plus z representing this path here. And then this one up here is, okay, z bar plus plus y plus this little thing, which itself is another parallel object. So it's the product of s bar with v. So this whole expression represents the hindrance of the total circuit from A to B. Now, Shannon realizes that because we can apply the algebraic manipulations that are contained in Huntington's Boolean algebra, in which Shannon spends a good amount of time studying and developing, we can simplify this kind of thing. Okay, and he shows how to do that, and eventually he gets the reduction that this same hindrance, say x from A to B, can be rewritten as w plus x plus y plus z times s bar times v. In other words, a situation like this. So there's w, and then plus x, because it's in series, then plus y, because it's in series, and then plus the product of these 3, z, s bar, and v. And so the effect is that if you build this circuit, and you build this circuit, and you have an operator who can turn each of the hindrances of the various ingredients on or off, then the effect of this circuit and the effect of this circuit are exactly the same. They will be open and closed under the same inputs, the same choices of whether we're turning these guys on or off. Okay, so you can see the power of this technology, being able to simplify circuits and analyze them efficiently through basically algebraic operations coming from, in this case, the Boolean algebra set up by Huntington. All right, so what are these reduction rules that Shannon is allowed to use to simplify a big expression like the one he's working on? Well, there are ones like this. So primary is this distributive law. X plus y times z is x plus y times x plus z. And I rewrite it again here because this is the non-obvious distributive law. This is the one that you haven't learned in high school, and so it kind of takes you a little while to get your head around it, but it's really just this second distributive law. Then we have De Morgan's laws, which Shannon sort of souped up to express what happens when you take the bar of more complicated or bigger sums or products. So if we have x plus y plus z plus and so on, we take the bar of this sum of a lot of different things, then we're getting the product of the corresponding bars of the individual hindrances. And conversely, if we take a product x, y, z, and so on, and we take the bar of all of that, then we get the sum of all the bars of the individual hindrances, x bar plus y bar plus z bar, and so on. And then we have these sort of special kind of absorption laws that x plus xy is x, no matter what y is, and that x times x plus y is also x, again, no matter what y is. And in addition, Shannon identifies two other kind of reduction laws, which I think are going beyond Huntington. They are these ones here, that if you have x times some function of x, y, and a whole bunch of others up to, say, z, then this is the same as x times f of 1 comma y comma z. In other words, you can take that second product and replace the x value there with just a 1. And there's a corresponding one here. So if you have x plus some function of x, y, and z, then that's equal to x plus the same function with the x now replaced with 0. Okay, I'll let you think about those. And so these kind of laws allowed Shannon to have a technology for being able to simplify big expressions like we just saw in the previous example. Okay, so if this was a course in electrical engineering, sort of a classical course that you find at universities or colleges, then we would spend quite a lot of time in developing skill at reducing things with this Boolean algebra framework. But my ultimate goal is to convince you that the Boolean algebra framework is not really optimal, that actually we're better off relying on the original algebra of Boole that came before the Boolean algebra and has since been largely, not entirely, forgotten in sort of mainstream education. So, but nevertheless, it's interesting to have some little experience. It's kind of fun to play around with Boolean algebra, which is important for other things. It's certainly important for set theory, right? It's a foundational framework for set theory. So there's no denying the importance of Boolean algebra and all these reduction formulas. But just for circuit analysis, we're going to be seeing that the algebra of Boole is a very powerful alternative. But here are some exercises just to play around with. So first of all, you can try to prove the previous rules that I just showed you. You can show this variant of the distributive law, that if you have x plus y, z, w, that's the same as x plus y times x plus z plus x times x plus w. And then you can prove this transposition property, that if you have x, y plus x bar z, that's the same as x plus z times x bar plus y. Quite pleasant. Okay, so that's great. So in our next video, we're going to move ahead in time past the development of transistors into the modern era where logic gates assume center stage. And then happily, Shannon's analysis just applies verbatim to the whole logic gate scenario and gives us a wonderful calculus to manipulate logic gates. So we're going to be talking about that next time. I hope you'll join me for that. I'm J Wildberger. Thanks for listening.